Hi everybody, welcome to video number 52. This is the last in a series where we've been trying to combine radar imagery with Landsat optical images to classify wetlands in the Middlebury, Vermont area. So to classify wetlands, we've been trying to combine three images: the radar, which is L-band JERS 1, with Landsat, and now we want to add in some elevation data. And we're going to get valuable information from all three of these images. So the workflows we've introduced in the past videos, the first one was to combine the radar and Landsat images into a multi-band raster that we could then classify. The second workflow, which we went through in the last video, was to actually use hue saturation value pan sharpening to combine the radar and Landsat images into a single 3-band image. Now, both these workflows involve another step, which is to apply an elevation mask, and that's going to be the topic of this video. The reason we want to apply an elevation mask is because wetlands are generally very flat-lying lowlands. By definition, if they're steep, it means the water can drain off and it won't pond and it won't be a wetland. So we want to develop an elevation mask. It's really a slope mask that's going to say, if the slope of the landscape is greater than, say, 5 degrees, then let's mask it out and not consider it in our wetland classification. Now this is going to be really helpful because this is going to automatically screen out a bunch of areas, and it's going to mean that the classification algorithm doesn't have to consider those areas when it's actually trying to break the image into different classes. And I'll mention also that this will be the last video of this series. I'll show you how to apply this mask, and then you're going to be on your own to actually run the classification scheme and try to delineate the wetlands. And I'll just remind you that videos 25 through 30 go through the process of image classification and post-classification procedures in ENVI. So in this video, we'll focus on how to apply a slope mask. So first, what is slope? Second, what is a mask? And then I'll show you how to compute slope in ENVI and apply a mask in ENVI. So what is slope? As you know, in 2 dimensions, slope is just given by rise over run, and it's a unitless quantity. So in this case, the slope in degrees is given by this angle theta, and it mathematically would be the arctangent of the opposite over adjacent, or A over B. In 3 dimensions, it's a little more complicated, and there's a number of different ways to compute slope. One simple way is called the 4 nearest approach, and basically what you do is you compute the slope in the x direction, you compute the slope in the y direction, and then you use the Pythagorean theorem to actually compute the slope as a function of that x and y slope, in this case 25.3 degrees. So as far as masking, what is a mask? A mask is a raster that has values of only 0 and 1 that you can use to screen out pixels that you don't want in your image. So for example, consider this image, which shows water in black surrounded by land in lighter colors. If we generate a mask for this, the mask would be a raster of the same size and shape. All the land pixels would have values of 0, and all the water pixels would have values of 1. Okay, we'd then take this mask and we would multiply it by the actual raster. So it would be a pixel by pixel multiplication of this times this. Values on the mask that had 0 would come out as 0 in the product raster. Values that had 1 in the mask would come out as whatever their original value was on the original raster. And this can be a nice way to get better contrast stretch and to limit the number of overall pixels you're considering in any type of analysis. So in this case, we will set areas with a high slope equal to 0 and mask them out. We'll set areas with a low slope that could be wetlands equal to 1, and we'll keep them. Okay, so let's head to ENVI. Here is our HSV pan-sharpened image. And I'd also like to mention that below that is in fact our combined radar Landsat 30-meter image. So I would invite you to classify either of these images. You've made them both in these two parallel workflows, and you're going to ultimately be able to classify either one, perhaps see which one gives you a better result. So we're going to make this elevation mask and apply it to both of these images. So we'll make the elevation mask from this data set, the SRTM of South Champlain Valley, which I've already added to the project. That's going to be in your elevation folder. So you can see that this extends way further than our study area. So before we do anything, I want to make a quick clip of this elevation image. And we'll do that under raster management, new file builder. Choose the DEM, choose spatial subset. Let's subset it by file. Let's go ahead and use this radar Landsat 30-meter. We'll hit OK, hit OK. I'll assign a file name. So I called it srtmclip.tiff, and I'll hit OK. And that happened very fast. I'm now going to remove the larger DEM. And you can see we've just got this patch of the DEM, and it perfectly overlays with our other images of our study area. Okay, so the next step is going to be to compute slope in this DEM. That's going to happen in the terrain tool set. We'll open that up and we'll go to topographic modeling, which actually contains a huge suite of topographic tools. We're going to do this on our clipped SRTM. So I hit OK. Now we could choose to compute anything we want. I'm going to choose slope, and we're going to choose the kernel size. That's going to be computed on a 3x3 grid, just like the example that I showed you. I'll specify a file name. Okay, that's srtmclip.slope.tiff, and it looks like we're ready to go. So one of the things I'm going to do next is go ahead and pick the crosshairs button here. And I'm actually going to patrol around and look at some of the slopes on this map and try to identify a range of slopes that seems reasonable as a threshold to define the wetlands. So I'm moving around, I'm seeing slopes of usually less than 1 in the wetlands. When I get up into the mountains over here, I'm seeing slopes that are often greater than 10 or even greater than 20 in some cases. So I think I'm going to pick a wetland threshold slope of 2. And I invite you to pick your own threshold slope, whatever seems good to you. Okay, so if you've got a slope threshold in mind, our next job is going to be to go ahead and use that to build the mask. So to build the mask, we'll go to raster management, build mask. And the first thing it's going to prompt us for is the number of samples and lines that we'd like our mask to have. So that's columns and rows. We want that to match our slope image exactly. So we'll go to View Metadata, and we'll note 447 samples, 336 lines. And we'll go back to Build Mask, 447, 336. Okay, so now we've told it how big we want this mask to be. Now let's give it some data to use. Go to Options, and we're going to import a data range. Notice that in past videos, we've specified the mask based on a shape file or a vector file. Particularly in the Lake Champlain lab, you remember we used a shape file of the lake to actually mask out temperatures. But in this case, we're going to import a data range. And we're going to import the data range from the slope image that we've created. And the minimum slope we want to consider is 0. I'm actually going to go ahead and consider a maximum slope of 3. This is going to leave me with a little bit more open area than if I use a slope of 2, but you're welcome to use whatever you want. I'm going to go ahead and try 3. So I'll hit OK, and I will specify a file name. So I've called this slope mask 3 to denote 3 degrees, and I'll hit apply. And there comes the slope map. You can see we've definitely masked out a lot of the steeper terrain in the mountains and a lot of maybe the bedrock ridges in the valley, and we've left open the possibility of classifying some of the lowlands in the valleys, which is likely to be where the wetlands are. So the next step is to apply this mask to either our pan-sharpened HSV image or to our stacked radar and Landsat image. Now remember, these have different spatial resolutions. Our stacked image has a resolution of 30 meters, and our pan-sharpened image has a resolution of 12.5 meters. And so to apply the mask to these images, we're going to need to resample the mask itself so it has the same pixel size as these images, because masking is a pixel by pixel calculation, so you have to make sure you have the same pixel size and that the pixels are lined up between the mask and the image that's going to be masked. So basically we need to resample the mask image again. And for lack of a better way to do this, we're going to use kind of a cheat technique on this, and we're basically going to repeatedly use the layer stacking tool. And we'll stack in the layers, and then they'll be resampled to the correct size, and then we're actually going to split them out again once they've been resized. So here we go. So why don't we start off with the pan sharpened image as well as the slope mask. So I'll hit Control, select both of those, hit OK. I'm going to reorder them so the slope mask comes after the 3-band pan sharpened image. We're going to leave it in the same projection, UTM 18, but we're going to downsample that slope mask from 80 meter pixels to 12.5 meter pixels. Very important, you have to leave this resampling at nearest neighbor. Because the mask is a binary, meaning zeros and ones, and it does not have any decimals, if we were to use a bilinear resampling, we'd end up with a lot of values between 0 and 1. But nearest neighbor will ensure that we just pick the value of the nearest pixel and preserve our integers 0 and 1. So I'll add a file name. So I've called my file HSV mask bundle. Just to remind myself, this is going to be a multi-band raster that has both the HSV and the mask raster in it. And I'll hit OK. So what's nice here, it's doing the resampling. Now our next step is going to be to actually split these bands out from one another now that they've been resampled. So to do that, we'll use the resize data tool, and we'll go right back to that bundle file we just made. But in this case, we're going to use a spectral subset, and I'm going to break out first just the mask band, which has now been resampled to a 12.5 meter pixel size. So I'm going to leave all this stuff the same, specify a file name. So I'm calling this mask 12.5 meter.tiff. I'll hit OK. It's going to split that out. And then I'm going to repeat that process once more, going back to the bundle. And now I'm going to split out the original 3 bands of that HSV pan-sharpened image. So I'll leave all this stuff the same, specify a file name, and I've called this HSV 12.5 resamp, and I'll hit OK. And while that's popping up, it always makes sense now. I'm going to get rid of this bundle file just so I don't get confused. And I'm going to get rid of it from my layer manager, and I'm going to close it on my data manager just because I don't need that anymore. So now we've got our resampled HSV and our resampled mask. I'm going to check the metadata just to verify that they have the same number of columns and rows. So this is 2884, 2168. This is 2884, 2168. So that's nice. They are going to line up really well now. For whatever reason, this is showing the mask as a single black image right now, but actually it is still made of ones and zeros. So my final step is then going to be to apply the mask. So I'm going to go down and hit Apply Mask, and I will choose as my input file my HSV pan sharpened. Importantly, I'm choosing the one I just resampled. Then as my masking band, I'm going to choose the resampled 12.5 meter mask. Now really importantly, if something's gone wrong in this process, and if the image and its mask do not have the same number of lines and rows, or lines and columns, or they're misaligned, it will not allow you to mask the image. So if the mask isn't showing up for some reason, you probably have a problem with your number of lines and columns. In any event, looks like we're ready to go here. So I'm going to hit OK. Then we'll choose a file name. I'm going to call this hsvmasked.tiff, and the mask value is 0. So in other words, make everything with a value of 0 dark, and we'll hit OK. Okay, so here is our newly masked image. You can see that all the masked pixels are now black, and all the pixels that were not masked are coming through in their original color. So just for a quick comparison, compare that with the unmasked image, and you can see we've really masked out a lot of the high terrain, and that seems to have worked pretty well. What you'll find is if you choose a mask of 2 degrees slope, you will further eliminate a bunch of pixels. If you choose a higher threshold, you'll have more pixels showing through. Okay, so your job now is to go back and repeat this masking procedure, this time on your multi-band radar Landsat image, this 30-meter image that we created in our second parallel workflow. Once you're done that, you'll have your 2 masked images, and you can play around with classifying either of them and figure out a classification scheme that's going to work best to draw out some of these wetlands, like this one, and this one. And there'll be more details in your handout. So just to remind you, in this video we talked about how to compute slope. We talked about the concept of a mask. Then I showed you how to compute slope in ENVI and how to apply a mask in ENVI. Please join us for our next video, number 53, Will Goes on Sabbatical and Joins a Motorcycle Gang. Seriously.